everybody, and welcome to Unlocking Enterprise AI Innovation. My name is Millie, and I will be your host for the webinar. Today, I'm joined by Simon Cottrell, Director of Technology from EB3, and Sonam Lama, Senior Solutions Architect at NVIDIA. So first, we're just going to go through our agenda. So first, Simon's going to provide us with an introduction to AI, and then he'll take us through some exciting demonstrations with NVIDIA NIMs and Mendix low-code application development. He will then take us through integrating enterprise data and any infrastructure considerations, and then we'll move on to a Q&A with Sonam. If anyone has any questions at any point during the webinar, please pop them in the chat and we will get to them at the end. So Simon, if you want to start us off, thank you.
Yeah, thank you. Welcome, I'm Simon Cottrell, Director of Technology at EB3. This webinar introduces NVIDIA NIMs and demonstrates how they can be utilised in conjunction with modern application development platforms such as Mendix, develop Gen AI enterprise applications. Many organisations are implementing AI for many different reasons, from improving product development to enhancing the customer experience. There is no silver bullet for AI. Many organisations have found this out while developing their own AI products. To implement AI, you first need to identify a specific use case and its associated business benefits. You then need data, an AI model, and compute. These are then supported by an organisation's business processes, their IT operations processes, and their IT development processes. An organisation then can realise an outcome. Sometimes, though, it isn't easy to define a clear business benefit as the technology is so new. Sometimes you just need to trust the ingenuity and enthusiasm of your employees when implementing a new technology. AI applications and our associated processes deliver the outcome and realise the value. Let's examine a standard generative AI chat-backed application, such as ChatGPT. ChatGPT is the application front end for the OpenAI GPT AI models. We can see when asked a simple question, we get a response. The response will appear word by word so that you can begin reading before the entire response is presented. This is by design, and the reasons will be covered later within the webinar. The reason why models are illustrated, as we've done so on the right, is they represent the model's neural network, with each node given a particular parameter weight. The largest Llama models have 105 billion parameters. In this example, we are using the model for inference, as the model has already been pre-trained. A model like Llama is trained on a curated dataset comprising of hundreds of billions of words. The training is run over 16,000 NVIDIA H100 GPUs and lasted for 54 days. Inference is the process of using a trained model to make predictions or generate outputs from new unseen data. Once trained, a model remains static and must be retrained to learn additional information. You need significantly less NVIDIA GPUs to infer against the largest Llama model, which is approximately 12. The generative AI stack can be split into applications, tools, and infrastructure. Use AI applications but have very little control over how these applications work, how they use your data, which models they utilize, and the underlying infrastructure they employ. Generative AI applications such as ChatGPT and Salesforce Einstein fit into this category. Tools are used to build generative AI applications, allowing you to control how an application is developed and which AI models are utilized. With cloud-hosted tools such as Amazon Bedrock and the OpenAI API, the underlying infrastructure is managed by the tool provider. Infrastructure provides complete control over where your AI applications are run, the models you use, and you can decide what servers, GPUs, storage, and networking are used to support your AI applications. What this gives an organization is choice. Sometimes choice can be overwhelming, though, especially when developing and scaling your own AI applications. A previous example of ChatGPT is an example of a generative AI application. You can build a custom generative AI chatbot application that utilizes the best AI LLM model for your chosen application. You can decide how the application is built, and you determine which LLM model to use. Many of the LLM models available can be consumed as a service and accessed through an industry standard API first developed by OpenAI. You can host your AI application in the cloud, and by using LLM as a service, you have the flexibility to choose your LLM model without worrying about the underlying infrastructure used to support the LLM model, as this is part of the service that's offered. You have the option to host your AI application on premise while still using LLM as a service. What if you want to host your own LLM model though, giving you more control over how your data is used and where it's stored? NVIDIA inference microservices allow an organization to host their own LLM instance. As LLM NIMs support the industry standard OpenAI API, your AI chatbot application can easily be migrated to utilize any number of the available NVIDIA LLM NIMs. NVIDIA inference microservices can be run from the cloud, or they can be run on premise using NVIDIA certified GPU accelerated server infrastructure. NVIDIA inference microservices are designed for secure and reliable deployment of AI models for inference. NIMs are fully validated for deployment on NVIDIA certified hardware and are fully supported in a production deployment when using NVIDIA AI enterprise licensing. Over 170 NIMs are available, and that number is growing daily. We'll now look at a demonstration where we go over the deployment of a NIM. You can register for a free NVIDIA developer account at developer.nvidia.com, which allows you to use NIMs for development and prototyping on up to 16 GPUs. You can also register for a 90-day AI enterprise trial license. To access NIMs, go to build.nvidia.com, where we are going to deploy the Lama 3.1 8B instruct model for our demonstration. You can test the model directly through the website or connect to an NVIDIA-hosted instance of the model from your own application. We want to deploy the model ourselves on our local workstation. Deploying a model is simply a matter of generating an API key, which we've previously done, and pulling and running the NIM using Docker. We're running the NIM from a local workstation equipped with an NVIDIA GPU that supports one of the smaller Lama models. To speed up the process, we've already downloaded the image to save time. We can now proceed with running the NIM. I've sped up this aspect of the demo as our chosen NIM can take a few minutes to initialize. Once ready, you can see the NIM is available for use and presents an example API request using curl. If we return to build.nvidia.com, we can see instructions on how to test the NIM. We will use Postman to accomplish this, which is an application that you can use to generate API calls. We've added a system message to instruct the LLM to present itself as friendly AI, provide concise answers, and say when it doesn't know something. We've asked it the difference between a comet and an asteroid. You can see the response took just under 2,000 milliseconds. In addition to supplying the response, additional useful usage information is also returned. A large language model processes text using tokens. The model learns the statistical relations between these tokens, which allows it to understand language and predict the next token in the sequence. This example shows how the response from the NIM in the demo may have been tokenized and indicates Terra tokenization for your application. You don't need to worry about this. Different models may use different tokenization algorithms. A rule of thumb is a token is approximately 3/4 of a word. Therefore, 100 tokens are roughly equivalent to 75 words. Most of the common LLM as a service offerings will cost the usage of the offering based upon the tokens used and the tokens processed. If we revisit our previous example of a custom AI chatbot application using NVIDIA NIMs, we sometimes need a more straightforward approach to developing a custom application. Mendix is a low-code application development environment based upon the principles of model-driven deployment, which can dramatically speed up and simplify enterprise application development. For many organizations, off-the-shelf applications only provide around 70% of the functionality they require. They have the option to either buy or build. Customizing off-the-shelf applications for requirements can be costly and time-consuming. Many applications, however, now have published APIs to allow customization integration with other applications from separate applications. Now organizations can buy and build. For many organizations, it's their custom applications that deliver their competitive value. Mendix provides a model-driven visual development environment that enables easy customization and extension of off-the-shelf applications. You can start developing and prototyping applications using Mendix for free by registering for an account at mendix.com. We'll now look at a demonstration of using Mendix to develop a simple chat application. For our demo, we're running a different NVIDIA NIM this time, the Mistral 7B Instruct LLM NIM. As you can see, we've already downloaded the model and we're already running the model. We will test, as before, the operation of the NIM using Postman. There we go. So as you can see, because we're using an LLM, different LLM, we get a slightly different answer from what we had previously. Mendix application projects are managed through a modern web-based interface and utilize modern agile development concepts. All development is done through the Mendix Studio Pro application. A demo application, Gen AI App 4, can be seen within the management environment. This was built using the blank Gen AI app available from the Mendix marketplace. We will now edit and run our application from Mendix Studio Pro that can be launched directly from the application management environment. The App Explorer on the left displays the components of the application, including the conversational UI and open AI connectors that we'll be utilizing. You can see the main homepage layout and the chat page layout. The chat page is built using predefined conversational UI snippets. The snippets enable the easy-to-use prepackaged collection of widgets that in this instance deliver the chat functionality. Microphones provide the logic for the application. The new chat custom widget is part of the Gen AI Commons toolset that allows system prompt to be defined and the name of the microphone to execute once the button is pressed on the chat. So we can see how we add in a system prompt, and we've used the same system prompt as we used previously. And this will also allow us to execute or action a microflow when the send button is clicked on the chat. These are all built for us that we're using as part of building the application. We can now see the microflow that's defined for when someone presses the send button, and we can see we've got the chat complete with history. If you want to, you can download directly the GenAI for Mendix toolset from the Mendix marketplace. Full documentation on how to use the conversational UI snippets and the GenAI Commons toolset are also provided. We can run our application locally from a workstation for development and prototyping purposes. First, we must configure the LLM provider and models we use. As NIM supports industry standard OpenAI API, we can configure applications to use our local NIM instance and specify a custom AI model name. In this particular instance, it's the Mistral 7B Instruct. Once configured, we can then access the chat application. You can see producing a simple GenAI chat application is very straightforward with Mendix and the provided tools and modules that are supplied through the Mendix marketplace. The knowledge of these LLM models is fixed once they are trained. This means that an LLM does not have access to an organization's enterprise data. This is often where the value lies, though, in being able to effectively and efficiently integrate large amounts of predominantly unstructured data. There are several ways we can achieve integrating enterprise data into our chat applications. You can train your own model, which is impractical and prohibitively expensive for most organizations. You can fine-tune a model, which, although more practical and cost-effective than training a model from scratch, is inflexible as the model tends to be outdated as soon as the training is finished. You can use basic prompt engineering, which involves finding the data yourself, convert it into plain text, and then sending it to the LLM along with the prompt related to what you're looking for. Although this works, it's not very usable. Function calling is a good solution when you want to provide the LLM model with access to structured data, typically through a REST API. Function calling, however, is not really that suitable for integrating large amounts of unstructured data. We then have retrieval augmented generation. RAG enables an LLM to access large amounts of unstructured enterprise data without requiring model training or fine-tuning. Function calling and RAG are two of the most common methods of integrating enterprise data into a GenAI application. If we revisit our previous AI chatbot application example using an NVIDIA LLM NIM, it cannot answer a domain-specific question about one of the latest NVIDIA GPUs because it wasn't trained on that information. By introducing a RAG pipeline to supply the domain-specific enterprise data to the NVIDIA LLM NIM, along with the original prompts, the LLM now has enough information to respond appropriately to the prompt and answer our question. RAG utilizes a vector database to store text embeddings and associated metadata, which can include access permissions, etc. The enterprise data is curated into text chunks that share context, such as a sentence or a paragraph. Another NIM, called an embedder, is used to encode the raw text chunks into embeddings or vectors. This NIM is auto-encoding NIM. It cannot generate, but it excels at classification and encoding, and is much more smaller and more efficient than the larger generative LLM models. The embeddings are then stored in the vector database for later retrieval. Text embedding is a way of representing words and phrases as multidimensional vectors based upon their contextual meaning. Similar phrases will have vectors that are close together, while phrases that have no commonality are much, much further apart. When a prompt is entered within the application, it is first passed through the same NIM embedder that acts now as a retriever. The prompt embedding is then compared with the vector database. The top matches are then returned. The successor RAG is based upon the quality of the embedding, which in turn depends upon the quality of the chunking and the quality of the retrieved matches. This is one of the most important aspects of NIM. This is often why a NIM embedder that has been fine-tuned based upon domain-specific knowledge can be used and delivers a better match. The original prompts, along with the top matches, are then passed the LLM NIM, and this gives the NIM the additional knowledge regarding the subject of the prompt. The NIM then generates a response and is then passed back to the client. To further refine the matches retrieved from the vector database, we can pass these matches through a NIM re-ranker. What this does is it further refines those matches against the original prompt. Much like a retriever, the re-ranker can also benefit from domain fine-tuning for specific areas. NVIDIA NeMo guardrails can also be used to ensure the prompt is appropriate and the response doesn't divulge sensitive information. Guardrails can also prevent against common LLM attacks, such as prompt injection and data poisoning. Many NIMs now include this functionality as standard. Mendix can support RAG through standard APIs when using a fully integrated RAG and LLM service. Alternatively, suppose you want more control over the RAG process. In that case, Mendix can be used to develop a more integrated application by using a Mendix vector database connector. This enables you to embed and retrieve data within the application. An embedding and retrieval LLM model is still needed, along with a re-ranker and the original generative LLM model. We'll finish with some comparison of two operations and looking at some considerations for the infrastructure you need to use to implement LLM NIMs. The application on the left streams the response as it's retrieved. So even though the LLM has not generated the entire response, you can still start reading the response. The application on the right takes the same amount of time to output the response, but waits until the entire response is retrieved. Which option gives the better user experience? The chat application on the left, application A. Which option uses the most resources? Both applications will consume the same amount of resources. But if we want to improve the latency of the application on the right, we will need additional resources to improve that latency. And given the fact that we can implement the applications in 2 different ways, is it worth giving larger, more amounts of resources to the application on the left and the application on the right compared to the application on the left? These are examples of questions we at Ebb3 can help you solve as you look to build GenAI applications using NVIDIA NIMs. How many concurrent sessions do I need to support? How does the application scale? What are the overall latency requirements? What GPU do we need to use, or what GPU is the best one to use given the vast range of GPUs available from NVIDIA? How many NIMs do I need to deploy to hit the number of concurrent sessions and my application latency? What servers do I need to use? Can this all be run from my chosen cloud? And if I'm going to support this on premise, how do I manage my Kubernetes layer? So Sonam Lama will now from a senior solutions architect at NVIDIA, now joins us if you've got any questions.
Thank you, Simon. If anyone has any questions about what Simon just went through, or any questions for Sonam, please pop them in the chat now. To start us off, could you please tell us more about NVIDIA Enterprise Licensing?
Sure. So NVIDIA AI Enterprise is how we take NIMs into production. For the purpose of just developing, as Sam correctly mentioned, you can just sign up with a developer account. And then you can freely use NIMs with up to 16 GPUs for lifetime. It's only once you take it into production that we require you to have a license, and that's so we can provide you with enterprise support in production. And list price for the enterprise license is $4,500 per GPU, or if it's in the cloud, it's $1 per GPU per hour.
Thank you. Sonam, I believe you wanted to mention about Blueprint.
Yes, that's right. So Simon's done a great demonstration on NIMs here. If you want to experience this further, you can go to build.nvidia.com. We have, I think, over 100, approaching 200 NIMs now. Many of these are open source. Some are from third parties. Some are built in-house at NVIDIA. But we also have what we term blueprints. So these are very broad horizontal use cases. For example, like RAG type solutions, a digital human. We have a video search and summarization agent. And essentially, these are one or more NIMs stitched together with community framework type solutions like LangChain and many other types. Like I'm not sure if Mendix is on there actually, but I wouldn't be surprised if we'll be collaborating in the future. And yeah, essentially these are pre-baked solutions where we'll give you, we'll tell you what kind of GPUs you'll need to deploy these solutions, but also we'll give you the reference data set. We'll also give you a notebook with the code to run this step by step, and then guidance on how to tailor and customize these solutions based on your own use case or your own data that comes into it.
Thank you. That is all the questions we have for now. Does Simon, Sonam, do either of you have anything else you wanted to discuss?
Not from me at this stage, but if anyone comes up with any questions, feel free to send them over my way and I'll get them back to you.
Okay. Okay, well, thank you very much for joining us, everybody. Like Sonam said, if anyone has any questions, please do feel free to contact us at any point and we'll get them answered for you. Or if you have any interest in what was discussed again, please reach out to us and we hope you enjoy the rest of your day. Thank you.